Thanks for the introduction. My name is Nitish, and today I will be presenting Tensaurus, which is a versatile accelerator for mixed sparse-dense tensor computations. This work was done as a collaboration between Cornell University, Microsoft AI and Research, and Intel Parallel Computing Lab. But first, let's try to understand what is a tensor. A tensor is a generalization of matrix to higher or lower dimensions. For example, a scalar is a tensor with 0 dimensions, a vector is a tensor with 1 dimension, a matrix is a tensor with 2 dimensions, and one can keep on adding dimensions to get a bigger and bigger tensor. A 2D array within a tensor is called a slice, and a 1D array is called a fiber. Many of the real-world datasets are represented in the form of large multidimensional tensors, and especially the sparse tensors. For example, here I am showing Amazon product review tensor, which consists of people, products, and product reviews. This tensor is extremely large and sparse and requires low dimensional representation for ease of understanding. Tensor decompositions are common methods to find low dimensional representation of such large multidimensional tensors. Two most commonly used tensor decompositions are CP decomposition, which represents a tensor as a summation of rank 1 tensors, and Tucker decomposition, which represents a large tensor using some factor matrices and a cotensor. CP decomposition and Tucker decomposition primarily consist of MTTKRP and TTMC kernels. In MTTKRP, a sparse tensor is multiplied with two dense matrices to get a dense output matrix. And in TTMC, a sparse tensor is multiplied with two dense matrices to get a dense output tensor. Thus, MTTKRP and TTMC live at the heart of tensor decomposition algorithms. As many of the real-world tensors are sparse and there are multiple tensor kernels, I will first show you how different applications domains lie in the kernel density space. Here on the x-axis, I am showing the density of the tensor in log domain, and on the y-axis, I am showing three representative tensor kernels. The solid black lines will represent different applications. For MTTKRP, we have recommendation systems such as the ones in Netflix, Facebook, and Amazon. These recommendation systems operate on very sparse data. Then we have CNN compression, where the densities are between 0.1 and 0.5. For dense MTTKRP, we have MRI. Similarly, for matrix-matrix multiplication, we have graph processing, graph neural networks, and sparse and dense CNNs. And for matrix vector multiplication, we have PageRank and sparse and dense RNNs. Now, if we look at the rightmost part of this spectrum, it consists of dense applications which are primarily compute bound. On the very left, we have sparse applications that operate on very sparse data and are primarily memory bound. And in the middle, we have applications which are kind of both compute and memory bound. Now, because different applications domains make use of different tensor kernels, have different sparsities and different compute and memory requirements, the existing hardware accelerators either just cover a single application or a small class of applications, while making some assumptions about the sparsity. Now, if we look at the spectrum of these applications, we will realize that the majority of them make use of either a sparse-dense tensor kernel, where some operands are sparse and some other are dense, or a dense tensor kernel where all the operands are dense. There are few cases in which this does not hold, and those are the sparse matrix multiplication and equivalently sparse matrix vector multiplication. Thus, in Tensaurus, we will try to cover a majority of these mixed sparse-dense tensor kernels. Now let's look at some of the challenges in designing such mixed sparse-dense tensor accelerator. We all know that accelerating dense tensor kernels is straightforward, and systolic arrays are probably the most efficient solution, which provide both high utilization of both compute and memory. However, for mixed sparse-dense tensor kernels, they cannot be efficiently mapped to these dense systolic arrays. Further, these kernels are memory bound, and it is very hard to achieve high compute and memory bandwidth utilization. Thus, the goal of this project is how can we design a regular accelerator which can also efficiently which can also be efficient for mixed sparse-dense tensor kernels. And the way we will do it is by co-designing a accelerator architecture and an efficient sparse storage format. By doing this, we will achieve low overhead of supporting sparse-dense tensor compute on dense systolic array and high compute and memory bandwidth utilization. Now, first I will introduce you to an efficient sparse storage format, and then I will talk about the co-design of the accelerator architecture. But first, let me motivate you as to why do we need a hardware-friendly sparse format. Let's take the example of a sparse matrix dense vector multiplication, or SPMV. The format that we use here to store the sparse matrix A is called CISR format, or compressed sparse row format, which is by far the most commonly used sparse format. Here all the non-zero elements of A are stored in the row major order in the values array along with their column IDs in the column ID array. And a set of row pointers determine the beginning of each row in these arrays. Now let's see the execution of SPMV on two P's where different rows of the sparse matrix are assigned to different P's. As we can see, in the first cycle, CSR results in non-contiguous axes in the values array, and the same is true for the second cycle. Thus, there are two major problems with CSR format. It results in non-streaming and non-vectorized memory accesses, and it requires indirect memory accesses. That is, it requires a read to a row pointer array, and which is then used to read the values array. The next format that I am showing is called the compressed interleaved sparse row format, or the CISR format. This format was proposed by Microsoft. In the CISR format, the number of P's in the hardware is known ahead of the time. In order to store the sparse data in CISR format, the first few rows are assigned to different P's. For example, in this case, row 0 and row 1 get assigned to P0 and P1. Then the non-zero entries from different P's are stored contiguously in the values array. For example, the first non-zero entry from P0 and P1 are A0, 0 and A1, and hence these are assigned to the values array. The corresponding column indices are then written to the column ID array, and because row 0 and row 1 are the first two rows assigned to P0 and P1, the length of those rows is also written to the row length array. In the next step, the next available non-zero entries from P0 and P1, which are A02 and A13, are written to the values array, and the corresponding column indices are written to the column ID array. And in the next step, since P0 and P1 ran out of the non-zero entries, the next available rows are row 2 and row 3, and they are assigned to P0 and P1. And their values are written to the values array along with their column indices in the column ID array. Thus, CISR format does a contiguous allocation of data assigned to different P's. Now, if we look at the execution of SPMV on this example, we'll see that in the first cycle, second cycle, and the third cycle, the memory accesses are always contiguous and vectorized in the values array. Now, if we compare the achieved memory bandwidth, we realize that with CSR format with 8 P's, we are able to achieve only 1.8 Gbps of bandwidth, while the peak memory bandwidth is 16 Gbps. While with CISR format, we are able to achieve 11.2 Gbps, which is 6x higher memory bandwidth utilization. Thus, the benefits of CISR format is it allows us to perform streaming and vectorized memory accesses. So, although CISR format helps achieve close to peak bandwidth, one of the major drawbacks of CISR format is that it is not scalable. Because of the row length array, it requires a centralized row decoding hardware to determine the row indices. To solve this issue, we modify CISR format such that the row indices are directly stored in the format along with the column indices, and we call such a format the CISR plus format. In the CISR plus format, the row index is appended in the row ID / column ID array before assigning the non-zero values from that row to the values array. In order to distinguish row IDs from column IDs, for each row ID, the corresponding entry in the values array is set to 0. This approach completely avoids row decoding, making the hardware more scalable. However, it has a slight overhead as it stores an extra 0 in the values array. This overhead, however, is negligible considering that an extra 0 is appended only once per row. Thus, we co-designed this sparse storage format, that is, to reduce the complexity of the hardware, we pay some extra overhead in terms of data storage. We further extend this format to multi-dimensional tensors by assigning different slices of the tensor to different P's and call it a compressed interleaved sparse slice or the CISS format. After designing an efficient sparse format, now we will try to design a common compute pattern for tensor kernels. But before that, let's take an example of MTTKRP and try to see what are the key components of such computation. For MTTKRP, we first take a non-zero value from the sparse tensor A and multiply it with a row from the dense matrix C and sum the results to get a partial result vector. We further take a row of B and perform an element-wise multiply to get another partial result vector. And then we sum these up to get a row of the dense output matrix. So if we try to abstract out the computation, we first pick a scalar, multiply it with a fiber, sum up the results over a domain, perform some vector operation with another fiber, sum up the results over a domain, and this gives us the output fibers. We call such a pattern a scalar fiber product followed by fiber-fiber product, or the SF cube compute pattern. The interesting thing about this pattern is that just by changing the domains D0 and D1, this pattern is capable of representing both dense and sparse tensor kernels. For example, in case of MTTKRP, by picking the domains as sparse domains, one can represent MTTKRP on sparse tensors, and by picking the domains as dense domains, one can represent MTTKRP on dense tensors. Further, other tensor kernels such as TTMC, MM, and MV are also easily mapped to this compute pattern. Thus, SF cube compute pattern can express all the common dense and mixed sparse dense tensor kernels. Now that we have designed a hardware-friendly sparse format and the SF cube compute pattern, I will use a bottom-up approach to describe the architecture of tensors. First, we use the SF cube compute pattern to build the architecture of a single P. It consists of a repeat unit to replicate the scalar data, a VV-mul unit to compute element-wise vector-vector multiplication, and a VV-add unit to compute element-wise vector-vector addition. Here, the non-zero scalar values from the sparse tensor, as in the SF cube compute pattern, are received from the left, and the fiber operands from the dense tensor are received from the top. The operations performed in VV-mul and VV-add units are shown using dotted arrows. We now observe that there is a coarse-grained parallelism in the SF cube compute pattern, where different output fibers can be computed in parallel. Thus, we scale the P's vertically, where different P's are responsible for computing different output fibers. We then realize that apart from the coarse-grained parallelism, there is also fine-grained SIMD parallelism within each P, where each P is performing a long SIMD vector compute. Thus, we split these long vector computations into multiple small vector computations and perform them in different P's by creating a 1D systolic network of P's. Thus, we scale the P's in a horizontal direction. We further use systolic network to communicate the sparse data across different P's. We further replace all the connections from P to the memory with the sparse and dense tensor and matrix load and store units, and insert scratchpad memories for caching the dense data. Thus, we can now push the sparse data through our dense systolic array efficiently. To evaluate the Tensaurus architecture, we implemented a cycle accurate model in Gem5. We also implemented the RTL of a P to get area and performance estimates. We used the state-of-the-art libraries SparseBlast, Splat for CPU, two sparse and parti for GPU, and a sparse neural network accelerator Cambricon-X as our baselines. We also used multiple datasets from different domains. For Cambricon-X baseline, we realized that it uses a CISR variant for storing sparse matrices, where empty entries are padded with don't cares, and a vector bit mask is used to identify the location of non-zeros. Thus, the sparse storage format is highly specialized for low sparsity, where the overhead of bit mask is not significant. Further, the CISR format in Cambricon-X results in load imbalance due to strict synchronization boundaries between different rows. Here I am showing the results on sparse neural networks of LXNet and VG16. We formulated the different column layers in LXNet and VG16 as sparse-dense matrix multiplications and executed them on CPU, GPU, and Cambricon-X and Tensaurus. As we can see, Tensaurus outperforms both CPU and GPU and Cambricon-X in both performance and energy efficiency for almost all the layers. Overall, Tensaurus is 1.9x faster and 1.7x more energy efficient than Cambricon-X, even for sparse neural networks. We further compared the performance and energy efficiency of CPU, GPU, and Tensaurus for MTTKRP kernel. For MTTKRP, Tensaurus has higher performance and energy efficiency compared to both CPU and GPU baselines in all the cases. There are more results. I would recommend you to refer to the paper for those results on different other kernels and datasets. Finally, to conclude, in this talk, I presented Tensaurus, which is a versatile accelerator for mixed sparse-dense tensor computations. It is also the first accelerator for sparse tensor computations, like MTTKRP and TDMC. It is versatile as it is not limited to just tensor decompositions, but also accelerates common matrix operations. It is adaptable in the sense that it can accelerate a varying range of sparsity, that is ranging from dense to very, very sparse. The key approach that we took was co-designing of sparse format and architecture, and we showed high band utilization and high speed up and energy efficiency over multiple baselines. So thanks a lot for listening, and I would recommend you to go and read the paper for more details. Thank you.